Right. Now we know both the two-dimensional wave equation in 12.9.1 and the boundary condition in 12.9.2 are linear and homogeneous. So a superposition of eigenfunction, okay, must be a solution of 2.9.1 and 2.9.2. Okay, so let's take the superposition here. So we have that. So any superposition such a superposition is satisfying these two equations here. Now, to satisfy the two initial conditions in 2.9.3 and first the initial conditions. The initial conditions in 12.9.3, we have f of xy should be equal to u xy 0. So we have summation n sine. So when t is 0, okay, when t is 0, when t is 0, sine 0 is 0, so we have cosine 0 is 1, so we have e and n here, and sine n pi x divided by a, sine n pi y divided by b. Okay, for all 0. For x in between 0 and a, for y in between 0 and b. So we have that. Okay, and which is the double Fourier sine series of the initial displacement. Okay, initial displacement f of xy. Okay. Even though we just discussed one-dimensional Fourier sine series expansion, but we can extend the theory to two-dimensional, even multi-dimensional Fourier series. Okay, so the idea is that because we specify we specify a function in this rectangle. So we know fx1 here. Okay? You know fx1. We can extend fx1 to periodic function, double periodic function in the plane. Okay? How do we do that? Well, we just divide. So we have okay, and we will repeat the pattern to here, to here, to here, right? So we will define the other function f star xy, okay, which is equal to f of x y for and f of star x plus a okay for all I think just only one would be enough. Is it okay? So this is the in particular if m is n are equal to 0, so they are 0 in this region. But if we and yeah, and we know this is true is because note that I think I have to from the boundary condition. F of xy is 0 for all xy in the boundary. So fs1 is 0. Okay, this is 0. So this is indeed periodic one, because when you move to here, you need that this boundary will be equal to the value in this boundary, right? The value here, and also the value around the boundary, around the line will be the same as here, because we want to repeat them. Okay, and for our case, from the boundary condition, the boundary point, at the boundary points, the f function are all 0. Okay, they are all zeros. Okay, so we have that, they are all 0. And okay, so that is the situation, and so that f star x1 is double the periodic function of in R2 is x period A and y period B. Okay, so we have that one, and so we can have okay. So you can regard f of x is just a period, all right? A half-range period. I think. Oh, I'm sorry. No. This is not what I want to say. Okay, it's not. Okay, the period should be in here. So, okay, I'm sorry. I have to extend a little bit. Okay, well, what is again? I need this one. From the boundary condition in 12.9.1, okay, we have f of xy equal to 0 for all xy in the boundary of R. Okay. Now, I should extend that. For here, I have minus. Okay. So I should have an arc. So okay, f star xy is equal to f x y in here. Let me put f x f star xy in here is equal to f of xy. Okay, good. F star xy is equal to f of minus x minus y. Good. Okay. And here f star xy equals minus f minus xy, and f star xy equal to minus f of x minus y. Okay, so I define f star in this region, right? And then so I extend. Originally I have f x y, right, in this part, and this is the full period. Okay, so the period is 2a, and this is 2b. I'm sorry, I have to correct. And okay, and then f star x plus a y plus b is equal to f star x y plus b equal to f star x plus a. So I think I can repeat. Okay, x plus a y equal to f x equal to f x y equal to f star x y plus b. Okay, so that's it for all x y. or that's fine. X. Okay. I think that's enough. So I have to modify my description. So I have to extend because this is just in one quadrant. Okay, just one quadrant here. So I have to extend that to a whole period of, and then f star becomes to a doubly periodic function in the plane. Okay, in the plane. So this is my expansion. Okay, this is the concept, and I can't delve into to develop a theory of double Fourier series expansion or double Fourier sine series expansion of that. Okay, but in principle I can do so. I can do so, but I don't need that because I can use one-dimensional Fourier series expansion to solve out my problem here. Okay. But I have to mention that the idea is that how come we can use double Fourier series expansion for a function defined just here, just around here, a rectangle. The reason is that we can extend such a piece information into a doubly periodic function with x period 2a and y period 2b. Okay, so that is the key idea. But technically I don't need that. All right. So let's start with something. Okay. So first of all, we deal with to determine. So we want to determine the coefficient E and N. Alright, so this is what we want. Because we have this identity here. So suppose we can expand f of x, y into such a double Fourier sine expansion, series expansion, then we can find E and N, right? So determine the coefficient E and N. We fix, okay, 1 as a parameter. Okay, so we fix 1 as a parameter and regard 12 point. So this one 12.9.11, I think so. 11. Yeah. Right. So this 9, 11 as Fourier sine series of f. Right, with respect to x, right? So I will expand E tilde m y sine m pi x a. Okay, all right. So I regard for each fixed y, f of x. It can be regarded as in the half range, in the half of a periodic function. Okay? And so the period is 2a, so this is half range representation. Okay? And the coefficient should be a function of y. Why? Because y is our parameter. So the coefficient should depend on y in general. Okay? With that expansion, so we know the coefficient functions E R E tilde m y r here E tilde m y actually is equal to summation n, well, E m n sine m pi y E Okay? So that is the coefficient function. Okay. So we have to find the coefficient function with the coefficient function, okay, and explain the coefficient function by the Fourier sine series expansion. Okay, and then we can find E and N. Okay, now the coefficient function is this one, and can be computed, right, by the formula U2 m 1 is equal to 2 divided by a 0 to a f of x1 sine m pi x divided by a and the dx. Okay, so we take the integral. Right? And so that's why it's a function of y. Because we integrate over x here. Okay, so now we find the coefficient function. So this coefficient function is in here. So now in 12.9.12, okay. Okay, in here is the Fourier sine series expansion of E2 times M1. Okay. And the coefficients E and N can be computed by, so we have E and N divided by B, integrate from 0 to B, E tilde M, Y, sine M pi Y, B and B1. Okay. Okay, and now we do the substitution here. So we have 2 divided by A, 2 divided by B, 0 to A, integrate 0 to B, f of x1 sine m pi x, A, sine m pi 1, dx and dy. Alright, so this is indeed the double Fourier sine transform. Okay, this is indeed the double Fourier sine transform here. Right, so you have that. So for now we can compute the coefficient by the initial expression here. Okay, so we can find that. So there is no problem for us. Okay, so we find EMN here. We find it. Now, our next job is to find E star MN. Okay, we want to find E star MN. Okay, but next, the partial derivative of the u, x, y, t. Okay, so where's y, t here? Oh, I need the equation number. So I need 12.9 for 11. So this should be 12. I have to change. So this is 12, and this is 13. 14. Sorry about that. Alright, so I need to recall this equation number. So the partial derivative of this u in 0.9 or 11 with respect to t is so ut x y t is equal to summation okay. So it's u m n t x y t. Okay. So this is equal to, and this is minus lambda mn e mn sine lambda mn t plus lambda mn e star mn cosine lambda mn t sine m pi x divided by a sine m pi y divided by t. So this is our velocity, and by 2.9.4, the initial velocity is gxy utxyt y0. Okay, so when we put 0 here, this term disappears. So we have summation lambda mn e star mn sine m pi x divided by a sine m pi y divided by b. 14. Okay, so we have that. And this time we have experience. Alright, so we know. That's so similar to we have the lambda mn e mn star, the coefficient. The coefficient actually is the double Fourier series, Fourier sine series. Transform gxy sine m pi x divided by a sine m pi y divided by b dx dy. Okay, so we have that. Because you can compare this one with this one. Okay, so the EMN here is played by the lambda m times E star m. Yeah. So we have that. And from here, you can know that this is the E star. Remember the eigenvalue are positive, right? Remember we have positive eigenvalue. So we can divide the eigenvalue here. Fine. Okay, so that's it. So we solved basically we solved our. So we have we know the EMN from the initial displacement. We know the E star mn from the initial velocity. Okay, velocity, and we know how to compute the EMN and EM star here by this expression and this expression. Okay, so basically we find a formal solution. Okay, so this complete the solution of 12.9.1 to 12.9.4. Okay. So we find the solution of the two-dimensional wave equations on a rectangular region with a homogeneous boundary condition and two initial conditions. One to specify the initial displacement. The second initial condition specify the initial velocity. Okay. And so we know how to solve it. Any questions? Okay, so now we consider the two-dimensional wave equation, right? For the rectangular membrane. But you know, membranes may have different shapes. Especially one very common shape is the circular membrane, right? Like a drum. See, right? Many musical instruments, for example, the drum, use circular membrane. Okay, so we would like to solve the two-dimensional wave equation on circular membrane. Now, with the circular membrane, how do we proceed our solutions? Okay. Right. So we should get some more experiences. Okay. And the key is on the Laplacian part. So the idea is we will look at a Laplacian in polar coordinate. Okay. So it's a general principle, okay, in boundary value problem for PDEs to choose coordinate. Okay, that make the formula for the boundary as simple as possible. Okay, so now we consider a two-dimensional circular membrane. For example, the drum head. Okay. So we will transform, right, the Laplacian in the wave equation. Remember I mentioned the Laplacian, right? Because the right hand side is just the Laplacian times the square of the speed. Okay, so we have to, when we consider a circular membrane, now a simple coordinate system for a circular membrane is the polar coordinate. Polar coordinate is much more simpler than the rectangular coordinate for circular object. Okay, as we know from geometry, So we will We will transform the Laplacian in the wave equation into polar coordinate. Theta. Okay, well, we have to specify such that x is equal to r cosine theta, and y becomes to r sine theta. Okay, and the inverse coordination is that actually r is equal to x squared plus y squared, and the theta x is arctangent y divided by x, where x greater than equal to 0, and arctangent yx plus pi if x is less than 0. Okay, so this is the and sometimes people just take arctangent by x. Okay, it's just a shorthand notation. Actually, arctangent what? Because tangent. Okay. Tangent function. Very interesting. Okay. Is pi 2, right? 2 minus pi and 2, and so this is okay. Okay. So if this is the theta, and this is tangent. And you may imagine that the tangent function, right, is from minus pi to minus infinity to infinity, okay, including the endpoint. So the arctangent, and we think about, is inverse, so it's 1 to 1. Okay, so inverse may be 2 minus pi. Okay, you can think about that as an extension. So this is 1 to 1. And so if x is 0, depends on y, right? So if y is positive, then this is positive infinity. And so arctangent becomes to pi over 2. But if y is negative, then this is minus infinity, so you go to minus pi over 2. Okay, so when x greater than equal to 0. So when x greater than 0, the angle, when x greater than 0, the angle should be from pi over 2 up to minus pi over 2, right? It's here. When x is positive. So when x is greater than equal to 0, the angle, this is the angle, right? The angle theta. So when x equal to, so when x is the angle should be in between okay, it's here. But if x is negative, then the angle should be in between here, right? It's around here. So when x is negative, the angle should be here. This is xy. xy. So when x is negative, the angle will be bigger than 90 degrees, but less than 270 degrees. Okay? So that's why we put pi here. We put pi here because the ratio, I just the ratio here. Okay, so I just make the theta, because the theta actually is from 0 to pi, basically. But you can think about that. This is from minus 2 pi to 3 3 pi over 2. Okay, so that is. So basically, you have that, except the origin. Okay, because the origin, but y equals to 0, the origin, that r equals to 0, but theta can be any value, right? So this is only one point you have to be careful about that. Otherwise, the polar coordinates is very good. Okay. Okay, so we will consider the coordinate transformation, and we will change the two-dimensional wave equation is basically in the rectangular coordinate system to two-dimensional wave equation in polar coordinate system. Okay, all right. So we will continue the discussion next week. By the way, I'm wondering, do you still remember the Laplace transform? Right? Did you learn Laplace transform, right? In OD, right? Okay, good. So I just need some elementary properties. So we will mention the method of applying Laplace transform to solve PDE, because some type of PDE is easier to solve by using Laplace transform. Okay, so I think I have to mention that next week. Okay, so our midterm number 2 will cover number 12. Okay, the PDE, and will be held December 7th. Okay, as our schedule. Okay.